Welcome to another episode of Learn to Code, Code to Learn. And this week, or this month now, we're going to be looking at I/O. If you want to know a little bit more about the series, and if you want to watch some of the earlier episodes where I explain in a bit more detail, but the backbone to this series is the 7 Languages in 7 Weeks book. And then what I've done is riffed off of that and converted it into 7 languages in roughly 7 months. It's in blocks of 4 weeks. Anyway, I'm going to dive in now and talk a little bit about basically what I've learned about the code so far. So second week I always do my reviewing my run through of the chapter in 7 Languages in 7 Weeks, and then sort of getting ready for the 2 weeks after in terms of refactoring code and maybe going back through stuff that I'm having trouble with, because some of the self-studying there I've noticed was particularly hard with this language, because I suppose part of it is the lack of the material out there on the web for I/O compared to something like Ruby, which we covered in the previous month. So let's dive in and talk a little bit about I/O and some of the things that I learned. I won't do everything, and this isn't just a retelling of the book. This is a representation of what I sort of absorbed through study and reflecting on the materials online as well. Now, all of the code, plus all of the code that I've created as a result of going through the chapters in the book, are on my GitHub repository, and I'll include links to that in the description and talk a little bit more about it at the end. Okay, so yeah, I was ably assisted once again by my virtual servitors, as you can see on the screen, Yowly McCatface and Socket Bestest Boy, known as Socks to his friends. He's not a chunky boy, but he does have a chunky sweater, so just, this look like I'd love a couple of sweaters like that. Look very comfy. So, moving on. A little bit about I/O before we dive in and look at some code. So it's created by Steve Ducorti, I think that's pronounced, in 2002. And that was after an attempt to assist a friend, Drew Nielsen, with another language, Cell. And it led Steve to explore language design creation. I think the idea was he thought he couldn't really help his friend until he actually understood how to create a programming language. So that's how I/O was born. It was an attempt to create a programming language. It's inspired by Smalltalk, Self, Lua, Lisp, Act, and Newton Script. It's known for its prototype-based object model, so they've sort of pushed out a distinction between instances and classes in the language. There are no classes. In I/O, everything is an object. So, it's like a lot of other object-oriented programs. It also uses dynamic typing, and programs are structured as trees of messages, which we'll see as we go in. It'll make more sense. The dynamic typing thing's super important, actually, because we're going to talk about how you can then sort of interrogate objects and clones to find out what types they are, or what types they have inherited based on how they're cloned. It also features actor-based concurrency and a small portable virtual machine. I'm not going to go through much in this episode about concurrency, but I will talk a little bit about it again at the end. New objects are created by cloning objects, and when a new object is created, differences between it and its parent are stored in the new object. Differential inheritance, apparently. Now, of course, you might not see that differential inheritance firsthand. It may be abstracted away, but there's methods by which you can, again, interrogate the objects in the language to find out, what might be going on. And I actually spent a lot of time doing that in this language, and it was super interesting to do that. So you'll see some examples as we go through of where I've deliberately put code in that sort of illustrates that. And again, if you're curious about the specific code I'm going to be using here, it's all in a folder which I'll explain at the end where you find that. And with this sort of stuff, for the content for the videos I'm doing, I always create a file, a language file called, what am I calling it? Sandpit. That's it. It's always called Sandpit, and then the file extension for the language. So general concepts. Objects are created by cloning other objects, which I mentioned already. Objects are prototypes. You might come across this term as well, proto. And objects being prototypes means that they can be used to create more objects. Objects are also collections of slots, and we'll look and see what a slot actually is. You'll start to realise, your light bulb will go on, and you can say, oh yeah, I can see what that, what they've called a slot might be referred to something else in a different language. Slots can be created and assigned in the same line of code. You'll get an error if you try and assign something to a slot without first creating the slot. Slots are also inherited by child objects from parent objects, again depending on how stuff has been cloned. And you use the name of the slot to send a message to the slot. There are various slots methods in the object hierarchy that can be used to inspect objects. And IO uses camel case in various ways, and you can see I've got a few different ways here for naming objects and slots. For example, if you want to indicate an object as a certain type of object in and of itself, then you start the name with uppercase, but we'll see how that manifests itself because there's some interesting differences. And here we go, we're diving into objects straight away. I thought it would best for me to front load objects in this video because it's so critical. So we'll get that out the way first, and then we'll look at ways in which everything sort of integrates. So if I wanted to create a type object from object, so at the very top of the tree, I'm going to clone this object called object. So object clone to create dog. Now notice here, it's dog with a capital D. All the colour coding here is obviously from me using a certain highlighter program in Visual Studio Code. And if you're interested in how I set up I/O, I did a video under the IT Wildcard banner specifically about this, which has gone out about a week prior to the release of this video. So yeah, I create my dog object just as a clone of object. Now if there happens to be any slots in there that are in object, they're going to get inherited by dog. The other thing is, you can see here, this has a capital D. We'll come on to that in a moment, why that's important. So if I ask you what type dog is, it's a dog. Okay, so what happens is, by capitalizing the name of the object, it's assigned a type of the object as the name of the object, as dog. If I then go on to create another object from dog, so use dog, and then create a clone of that, so sort of prototyping. Notice here, I'm going to create an object called rover. Now here it's in lowercase. So clone of dog, rover. But this time if I ask it what the type is, it's a dog type. It's not a rover type. And that's because I chose not to capitalize rover. If I'd done a rover with a capital R, it would have returned rover as the type. So that's one of the first things you need to establish in I/O, is this business with the objects. If you capitalize the name of the object, that becomes its type. If you don't, then the type comes from the object from which it was cloned from, or if that object also happens to be a non-type object. It just keeps going up the tree till it finds a type object, and that's the type. We can create a non-type object directly from object. I'm choosing to call them non-type objects here. There might be a better term. And just to show how that works, here it returns object. So where I used object as a clone for dog. It was capital D. The type is dog. But here, NTO, short for non-type object. I just had to call it something. It returns object because it's lowercase. And so it doesn't inherently, I think that's the word I'm looking for, it doesn't inherently have a type. Its type comes from the thing it was cloned from. And you can see here I'm using the type here in this print ln to do it. Now notice how everything looks a little bit back to front here. We're not using sort of, dot notations on objects to do methods. We're not having, for this example, we haven't got, say, a particular method or function, and then we bracket it. We got brackets around it, so it's not like got a certain type of functional look to it. You might see here. You're actually sending a message. So print ln, that's a message to type, to Rover. And you have to sort of think about this in the order. It becomes important in a moment when you're thinking about how to make sure it's sending a message to the right thing. So basically the message is we want to print the type of Rover. So I read these from right to left usually in terms of working out what is messaging what. Okay, now onto slots. So how do you create, assign, update, find a slot? So supposing we've got our object dog, which we've already created, we've already cloned from object, and we want to create a slot called breed. That's how we do it. So dog breed, here's this symbol. Now notice the difference between this and this. So let's try and unpack this, explain what's going on here. So you've got dog breed, and you're going to assign it the value, or the message, I suppose, unknown. So this is the thing. Assume when I'm talking about assigning, or if I say things like, values or whatever, if I'm speaking strictly as a way you should think about in I/O, it's a message. I'm sending a message of the word unknown to breed, assigning it to breed. So in dog, breed becomes unknown. Now what I can do is, because I've created this in dog and breed was cloned from dog, the slot breed is also available to Rover. And what happens here, in the grand scheme of things, is I assign the word mutt to breed, and it looks at Rover, can't find the slot for breed there, or the slot name. I haven't specifically defined it, but it's available there as its own slot. But I haven't explicitly said Rover breed is created. So I didn't need to create breed. It was all created. The slot was already created because it exists in dog. So now I just use this to simply assign mutt to the breed in Rover. But I could equally create a slot specifically called age for Rover, and that would only exist in Rover. So whenever you go to assign a slot, if you don't create it, like we have done here with using this colon equals, it checks to see, is the slot on the object, or is it a slot that it's inherited from something it's been cloned from. So now if I was having to check these to try and print breed or rover, I would find that dog breed, so if I did dog breed print ln, it would return unknown. If I do rover breed print ln, it will return mutt. So assigning mutt here hasn't overwritten, obviously, further up the tree. And I can find out slots on objects, and that will show me, what slots are there, what's, been passed down, those sort of things. And, similar thing here, if I want to take NTO, which I've previously created that object, create a slot called description, update it at the same time with this small shiny thing, and then I can go on later and I could update the description slot on the NTO object to be a marble instead. So yeah, that's how slots very simply work. Now, of course, what you can pack on a slot, what you can send to a slot, is pretty much everything, as we'll see in a moment, or a lot of stuff. But before we start to do that, again, let's try and weave this. Let's talk a little bit about conditionals. So in I/O, conditional statements are used to pass different messages based on certain conditions. Here are some examples of conditional statements in I/O. So there's the usual suspects, or the usual suspect of if then else in the form if, and then you can see we've got open brackets, the condition, the do message, and the else do message. The else part is optional. The condition is considered false if the condition expression evaluates to false or nil, and it's true otherwise. There is another form where you can do it like this, so each one's separate. So you've got if condition space then do a message, else do a message. And again, when I'm talking about message here, that can be a whole load of things. It's not like a text message. Yeah, just we can have methods on there, we can have conditionals on there. Yeah, you'll see in a moment. Also, the else if form as well, you can see. So if then, else if, can check another condition, then, else, and so on. There's comparison methods available. They return either true or false, so equals, not equals, so greater than equal to, less than equal to, greater than, less than. There's also a compare method and small talk style if true, if false, if nil, if non-nil methods are also supported. So let's look at some of these in situ. So, a couple of things, well, more than a couple of things I can do here, but yeah, I'll just show you two. So one thing I could do is just pretty much straight like this. So I could do if rover age greater than 2, because I've already got an age slot. So it's basically checking the slot here to see, is the age slot on rover less than 2? If so, it's a pupper, or that's the piece of text, the string that I'm going to generate. Else, non-pupper. So here the message is pretty straightforward, and then I'm going to print that. So evaluates this, and then I'm sending the message to print whatever this evaluates to. And of course within this, as was highlighted, you can think of these as messages inside of here sending to these other components. I could create a slot is pupper on the dog object. So to do that, I could do dog is pupper, and then here's the both the create and the sign at the same time, and then put that there. So now if I ever want to do this check on any object that is cloned from dog or is dog, or clones of things where they would inherit the slots, I can do this. So Rover was a clone of dog, so I should be able to do this. So Rover is Papa print Lynn, and it'll do this now. So that's now locked into that slot. Now, of course, here's where it gets interesting. IO is dynamic, so I can play pretty fast and loose within reasons, but yeah, still pretty fast and loose about what I put in slots, what I choose to put on a slot that replaces something else. So assigning something else to a slot. Maybe I could just put, dog is Papa equals yes. Or true, those sort of things. But I would say in IO, when you're learning it, just try and notice the routing of the messages. What slots are receiving the message? Where are those slots? Have they been inherited from other objects in the tree? That sort of stuff. And then as you start to learn that messaging hierarchy, it'll get easier in the language. So, conditionals. Let's talk a bit about this other conditional, compare. So, supposing I've got, and here you can see, we've done something here, and I'll come on to this actually down here. You can see this object called lobby. So in IO, you can do stuff like this. I don't have to assign. I don't have to make, create. Create A and B necessarily are as slots on a specific object, but they do end up on an object. This lobby object. So, which is just built into the language. So if I just do this without referencing anything, no dogs, no rovers, no NTO, whatever objects I've chosen to create myself. So here A is 10. So I'm, creating an A slot and assigning 10 to it. Here, creating a B slot, assigning 20 to it. I'm doing a comparison here. So sending the compare B here. This is built in. And this is a message to A, saying to A, I want to compare you to B. So, and I'm going to actually assign that result because I want to just talk about what's happening in these different places. So, if I was to print the comparison result, it's -1. And that's because the compare method, as I've set up here, returns -1, 0, or 1 in the case of less than, equal to, or greater than. And if you're curious about where the slot names are or types, you can do stuff like this. So lobby, slot names, print ln, and I'll find all of these. So these are all these ones where I didn't give a specific object qualification here. It's put them on the lobby. I can also do things like this. So compare is just in a in object. It's also in number as well. So when you're doing IO, when you're working in IO will sort of work out whether that slot exists. So interestingly enough, these slots are holding values. These slots are holding some sort of method. I can also find out, what actually is A. When I created it, what did it do there? So it's put it in lobby, but it's actually a number object as well. So again, you can play around in the language. Okay, well, what if I have a look on slots on number? Yeah, that sort of stuff. It's really fascinating. Become a detective in this language. Small talk style conditionals. So this sort of form here. So again, very interesting once you sort of do out these sort of things. Again, if we were to try and interrogate various objects, we would find out that these are being created in the lobby object. There's slots on the lobby object. And if I was to try and work out what's going on here, so we start off where y is assigned, y has its slot created, it's assigned 4, x's slot's created, it's assigned 6. And if I do this evaluation, so what am I doing here? Well, I'm going, is y, so y greater than, sorry, I keep getting it wrong, y less than 10. So is that true? So y is 4. So if it's true, then I'm going to make x equal to y. If it's false, I'm going to make x equal to. So now if I look at the contents of the slots, you can see indeed now y and x are 4. And z here, because I decided to check that as well and create a slot, assign it, is true. So it's returned true, which is why it did the if true. And again, it's interesting to play around with various pieces of code just to satisfy your own curiosity or to curb any insanity, I suppose. So loops. There's a loop method that you can use to set up a loop. You can break out of it. Obviously, if you don't choose to break out of it, then you end up with an infinite loop, and you've got to obviously Control-C out of it, or whatever the break is in your IDE, or whatever you're running it in. And then we've got repeat, the number repeat. So it's a number method. Okay, so it's a method on number, but it's just available to use, and it can be used to repeat a loop a given number of times. So I'm just using the term here, object messages stuff, because as long as it's syntactically correct, you can stick anything in here, and of course you can run over multiple lines, which we'll see in a moment how that works with some examples. But yeah, so we've got object stroke messaging stuff inside of there, whatever we choose to do. Then while is in the form this, so while we've got our condition, and then whatever message we want to do, as in terms of what messaging actually means in I/O. And then we've got for in the form for, a counter, a start, an end, an optional step, that's how much you want to go up each time, and the for, and then the do, what you want to do at the end. Again, this do could contain quite complex set of messages on messages and objects and various other things. Conditionals and any part of syntax. Again, there's anything that's syntactically correct in that situation. Also things like break and continue, which are very useful in the context of several of these loops. So the loop, repeat, while and for support the break and continue methods. Also, I might as well bring up return here. So any part of a block can return immediately using the return method. So any block of code, not just functions, and it's rather like Ruby in terms of functions, which we'll see. You can opt in a function to leave out the return if it's obvious where, what's going to be the last piece of code that's going to execute. The last message that's going to occur before the function finishes. Or should I say function? I meant to say the method. And just a note here, which I think I got from the guide, the IO guide on the website. So internally break continue return all work by setting an IO state internal variable called stop status, which is monitored by the loop and message evaluation code. So some loop stuff. So again, some of this stuff could easily be refactored, but I've just spread out stuff or done it in a certain way, just so you can actually see a bit easier what's going on if anybody watching this isn't used to reading code or isn't familiar with simplifying certain things in code, like incrementing stuff like that. So I've put this in sort of slightly more extended form. I've also tried to make sure that the variables I'm using are fairly descriptive. So here, just a loop. I'm setting count again. Yeah, we're creating a slot in the lobby, creating and assigning it 1. We're then looping, and here you can see that loop. So you can sort of see here we've got multiple parts going on here. So I've got the loop, I've got the condition, I've got some sort of message that I want to do here based on this condition. So if I'm doing this thing where I'm just basically checking to see if it's divisible by 2 without any remainder here. So you'll recognize if you do other programming, there's certain symbols that you'll recognize, but that's what's going on there. So again, my comparison operator is different from my assignment operator. Fortunately or unfortunately, depending on how you think about it. And then it goes on. If that's true, then I'm doing this. And at this point, I'm just going to continue with the loop. And then outside of that if statement, I'm going to do a print line on the count. I'm then going to increment the count, and then if the count is greater than 10, I'm going to break. So in a rather convoluted way, what this is doing is going through and printing out even numbers in here, or creating even numbers. But I was deliberately convoluted here because I just wanted to show that, I can take loop, which looked fairly condensed on there, and have all these components inside of it. You can see the brackets here, and I've got multiple if clauses, some of which have multiple parts in them, some of which don't. I can use a repeat method, as I said earlier, so this is what the repeat method looks like. So I'm just asking it to repeat this part 5 times. So again, the way of thinking these messages is I'm sending this message to 5, and I'm sending this message to repeat. Really. So I could turn this into a slot on the dog object as well, if I felt so inclined. So dog doing bark, create and assign the slot doing bark, assign it far, assign it this, the whole thing. So now if I do rover doing bark, it's going to look for doing bark on rover, doesn't see it there, but it is in dog, which rover is a clone of. So it'll go ahead and do the bark 5 times. Well, doing a bark is 5 woofs. And then a while method. So just a simple countdown here. Counter set to 10 while the counter is greater than 0. It'll do this. So all the time that's true. This keeps looping round count as being decremented by 1 each time. And again, these are slots, so on. This is the condition. These are the messages. I think you get the picture. And the for method. Now, what's interesting here is you can see we've got several different examples here. So the start and end messages are just evaluated once when the loop starts. So we're going to go through this, and we're taking n and just doing a for loop from 0 to 10, and then printing out that for loop. Printing out n each time in there. And again, you can run this code to see what that actually does. In this particular example, if you were to run this, it actually does go all the way up to 10. So it does go from 0 to 10, so they're totally inclusive in both numbers. Other for loops in other languages don't always do that. Here's an example with a step. So I can do the same but put a step in here. And so it's going to start at 0, go 3, 6, 9. But I can also do negative steps. So I can start with 10, go back to 0, and that will count from 10 down to 0. But once again, of course, I can choose what I want to do in here and make it as complex or as simple as I want, as long as I follow IO's syntactic rules. And as I mentioned, any part of a block can return immediately using the return method. I've put this in with the loops, but here you can see I can actually do it within a method as well. So I can do return from loops, I can do return from methods, and that will just return to wherever it was. So here what will happen is it'll definitely print this bit. It'll return this bit. This bit will get returned. And then it won't do this. So if I do test return print ln, I'll actually get this is done, this is returned as one big long thing. Here, if you use the word print as opposed to ln, it's just print without the line feed. So in IO, an operator is just a message whose name contains no alphanumeric characters other than some cases here, or is one of the following words, or and return. Standard operators follow C's precedence order. User-defined operators that don't have a standard operator name are performed left to right. And here's the kicker. So operators can also be added or removed or have their precedence changed by using the global operator tree table object. IO has 3 assignment operators. So this one creates a slot, creates a setter. So it creates it as a setter, which means if you were to clone that object subsequently with that contain that slot, it would also set whatever variable, whatever. It would also set variable. It would set whatever message, whatever value you'd assigned as well. This just creates a slot and assigns a value, which is mostly what we've been using so far to do that. And then this one assigns a value to the slot if it exists. Otherwise, you get an error, you get an exception raised. So if you want to see the operator table in IA, you can do the following. The closer to 0 bind first, it also lists the assignment operators. And I'll show you what the table looks like in a moment when we get on to the next slide. And also how to add new operators. So that's what this looks like, and it will print out the operator table with the assignment operators and a very succinct how to add new operators, which is a little bit more complicated than it actually alludes to, and we'll come on to that in a moment. So let's suppose we want to try adding a new operator and setting a precedent. You can also override an existing precedent as well. So we're going to create this operator called XOR, which isn't currently on the operator table, and that's how we add it. We can now implement the XOR method. We're going to just use it like they showed in the book, just using brute force to keep it simple. So doing this, creating these true or false sort of XOR methods will implement the XOR method. So now I can test them, and if I was to run this code, everything should be correct for XOR. So true and true would be false, true and false would be true, false and true would be true, and false would be false. So if it's the same, it comes out the false. If it's the same, if they're both the same, it comes out false. If they're different, it comes out true. And if I was to have done the previous one, this operator table print ln, this is the first part I get. So here's my precedence order. Here's them. Now, if I'd done that prior to me updating the table, as I have done here, XOR wouldn't be here. If I'd done it afterwards, then I would have seen this added. So of course, if you're doing this, good idea when you're experimenting, seeing what your code does. Always check before and after, just to make sure you can see what's going on. So you can see how everything's positioned on the operator table. Further down, you get the assign operators table part. This is what it looks like, and then instructions on how to add a new operator. Notice also you have to implement in some way, like I did here, that to do whatever it is you want it to do. Okay, comments, pretty straightforward. It's lines of annotation with II code, like every other language that has comments, ignored by the interpreter. Used to provide additional information or explanation about the code, such as its purpose, logic, or usage. So we've got this form if you want to comment out a group, for example, and there's also this style as well. So, and the other thing you can do is, because you can just use this over multiple lines. So you can use it to add a comment to a line, use it above a line, below a line. I even tend to use this just on multiple lines myself, but equally I could use this. So, abstraction in I/O. So all abstraction is just the hiding implementation details of a system or component and exposing only essential features or functionality to, the user. Now, you've probably seen already how that's already just a thing through, playing around with objects and what we played around with slots. Once you've created that and abstracted it away, as long as it works correctly, you don't really have to care about what's going on in the background. And abstraction in the broadest sense just helps to simplify code, reduce duplication, improve readability and maintainability. In IO, abstraction is achieved in various ways through prototypes, which is what we've been doing mainly so far. So objects are clones of other objects, and they can serve as templates that hide the complexity and allow for the creation of new objects with the desired behaviours without exposing internal workings. And of course, the whole inheritance structure works through that. You've got methods, which encapsulate behaviour in IO. And when you define a method, you're providing an interface for other parts of your program to interact with. The internal logic of the method is hidden from the caller, who only needs to know the method's name and the parameters it requires. And then you've got dynamic typing as well, sort of interface with it, because IO is dynamically typed, which means the types are associated with values, not variables. So it allows for more flexibility and less concern about the data types being manipulated, which can be seen as a form of abstraction. And I noticed when I was programming the language, more than any other language where that I've used that has dynamic typing, I was sort of caring less and less about the typing. And it's just so dynamic with this ability to just, 1 minute a slot can be doing one thing, and then next minute, if you've reassigned it something else, it's something completely different. And so that whole message passing thing, as it says here, everything is done through message passing, which is a way of requesting behaviour from objects. And the message system abstracts the communication between objects, allowing for more modular and flexible code. So yeah, I definitely found myself forgetting myself in the language a little bit when I was using it. So let's look at some abstraction here through methods, and something we haven't looked at yet, which is how we can create a whole load of methods on an object, and sort of all at the same time. Now you can break these down. You could just create your dog object and then individually create the slots in similar ways to which we've seen already. So I could create a clone of the object called dog, and then further on in my code, create a slot called bark, create a slot to prompt to feed, create a slot called bark 5 times, then prompt. But I can also do it this way. So just clone the object at the same time, do all of this. So there's a do there, which we haven't come across yet. So a good way of creating a block of code or a block of messages in any critical place where you need to do that. So we've seen lots of opportunities to put messages in places. So we can create our bark method this way. So it's just bark and then print line. Prompt to feed, separate method which prompts the feed question, do you want to feed the dog? Yes, no, uses this. So we're creating a file object. Sorry, I have to think about this. So we've got this answer here, which is our file object with the standard input slot, and sending the read line message to that standard input. So, again, a message to a message to a message, and objects in between, and slots. So then once we've got that on in that slot, we can then send these other messages to that slot. So if the answer as lowercase, so we've sent the as lowercase message to answer is equal to yes. So that's what we're going to do. And then the bark 5 times method. So repeat the bark 5 times if the prompt to feed is not, so it's not prompt to feed, and if that's the case, then bark 5 times, then prompt. So there's a recursion going on here. So behind this, what's going on is the dog's obviously barking for food, and if you feed the dog, it stops barking. But if you don't, if you say, no, I'm not going to feed you, or you don't say yes, then the dog barks 5 times again. So, yeah. So I just wanted to illustrate examples here of where, you're creating methods and then you're using methods within those methods, all through this sort of messaging and cloning that's going on. So then we come to use a method and we just do dog bark 5 times, then prompt, and it just takes care of that. It's abstracted away all these component parts in the language. And I can do more common things you might recognize, which is things like factorial. So I can define a method, and if I do this, then it's just going to not attribute it to any, I haven't specifically given it an object to create a factorial slot on. So it's just going to create it in the ways that we've seen already if you don't do that. So yeah, just a method here for calculating factorial. Now, I'm assuming it's already in the language anyway. So, but just if you're curious, what that might look like in I/O. So yeah, it's clearly here I'm telling it, yes, it's a method. And of course within here I've got other things that I'm having to create slots for within this method, like a result slot, to be able to have this value on it and assign it. So yeah. And then as I mentioned in the Ruby one, obviously at some point in all of this I'd want to have some sort of error checking code to handle negative factorials and put up, give back an appropriate reply for those instances. And just I've got to decide where I'm going to put that checking code. Do I build it into the method itself? Do I have another method and I want to use? How am I going to do that? We could also use recursion in I/O. That's what recursion would look like. And if you're used to recursion in other languages, fairly straightforward. And here you can see how I'm, calling the method when it's been defined like this, when the factorial slot's been created like this. There's no mention in here of any associated object. We could also use range as well. There's a range thing which we'll come back to in a moment later on. Another non-recursive style. And with this one, you've got to be careful. I have this here because if I don't, I get weird results. If I just leave this, it's going to try and return values from evaluating this. And yeah, it comes out super weird if I do that. So here, I could put return here if I wanted to. But again, structurally, you can see here how the ifs are sort of broken down. In fact, I probably should have. Oh no, I'm okay. There, yep. So here we've got if spread out. Here, I've opted not to. I could have condensed this down if I so chose. And that's again the thing. It's up to you whether you want to have these sort of fancy one-liners, or whether you want to sort of indent it, break it down in certain ways. I've noticed that I/O doesn't really care too much about indentation. I'm tending to, my code highlighter software that I'm using is defaulting to 4 spaces. So that's what I'm using here. Okay, types in I/O. So in the I/O programming language, types and type checking are handled dynamically. I/O is a prototype-based language, which means that it doesn't have classes like many other object-oriented languages. Instead, objects are created by cloning other objects which serve as prototypes. You notice there's a lot of repetition in this presentation in this video, just to hammer home this whole idea if it's something you're not familiar with. Type checking in I is not as strict as statically typed languages because IO is dynamically typed, and it means that types are associated with values rather than variables. For example, you can have a variable that at one point holds a number and later holds a string without any error. Now, here I'm slipping backwards and forwards here when I'm putting this together, but here we're using the term variable, but we're talking about a slot here. You might want to play around with seeing how IO handles types, so you can see how you might want to deal with potential problems in your code. Because it's so dynamic, it's really, like I've said, I've completely just lent into it and forgotten. And in the language I've been playing really fast and loose with slots, and 1 minute it's one thing, next minute it's another, next minute it's doing something completely different. So yeah, just be super careful. So just a few notes on what happens if we just check the types on things, and by using this type command. So the value of 3. So here I've just got a value which is a slot. I'm just creating the slot in the lobby, because if you remember, when you create a slot and you don't reference an object, it just creates that slot in the lobby object, or on the lobby object, I suppose. So this is a number type. This is a sequence type, hello, interestingly enough. Lists look like this. True. Value is now type true. Value is now type nil. So all the time, I'm just, like I say, playing fast and loose with the dynamic typing. It's gone from being a type of number to being a type of nil, and it's not going to bark at me if I was to run this code. Again, you can see all this in action if you use the sand pit. Numbers, those are valid numbers. Hex numbers are also supported, and you can again play around with the casing as well if that is indeed a thing for certain of the hex characters. But again, I encourage you to play around. What I'm hoping to do with these series of videos is not give you okay, now you know everything about the language. That's probably apparent. But I want to try and encourage you to play with it. I'm probably going to say things here that are wrong, incorrect in some ways, or don't apply in all circumstances. I've tried to, fact check myself as much as I can and make sure that I did actually read the book correctly. And, I've tested code numerous times, but I'm going to make mistakes. But that's the same when I think you look at any source. I was checking one of those cookbooks the other day, and there was a glaring problem in one of the published cookbook, which the code just wouldn't have worked properly. And I don't think it ever worked. I don't think it was because it was a deprecated thing. And this wasn't specifically IO, it was actually in another language, which I was a little bit more familiar with. So I encourage you to try this stuff out. Check that this actually does work. In the comments section, if I've done something really stupid or said something that doesn't ring true, and you've either tested it or a bit of IO, please correct me. Because the whole point of these series is, like I said, that it's supposed to be me exploring my own sort of learning domain in real life as I go along learning this stuff. So strings. So strings can be defined by a single set of double quotes with escape quotes and other escape characters within. Something like this. You can do a trick with triple quotes where you can use it to expand multiple lines. It also lets you use characters without escaping. And the normal problem you get with strings is this is a classic one where you want to use like speech marks, double quotes, when you've already used double quotes to define the string. So there are also various methods for performing string manipulation. Now, I'm not going to go through all of them, but you can probably guess. You can find out about them by doing interrogating the slot listings on objects and seeing what's in there. Is already really useful. So, you could interrogate the string object, or as we, I think it was called the sequence object. I think it was, yeah. So in I/O, you'll come across, if you ask, a string what type it is, or something you think's a string, it'll say it's a sequence. So, and this is straight from the website. I checked this. So an immutable sequence is called a symbol, apparently, and a mutable sequence is the equivalent of a buffer or string. I'm not quite sure at the moment in I/O exactly how immutability and mutability work. It's not something I've got a clear idea of. Like if we were talking closure, I'd have a lot clearer idea, or Rust, for instance. In I/O, it's not something I've really had to tackle too much so far, because I've been playing fast and loose with types and other things. But yeah, just flagging it up there is something you can play around with. So mutability, immutability, and the fact that strings are referred to as sequences in this particular case. So we have lists in here, so an array of references, and supports all the standard array manipulation and enumeration methods. Again, you need to interrogate. I find when I was working in I/O, I was doing a lot of interrogation of I/O using, interrogating the slots on the objects. So we can create a list, an empty list, by just cloning the list object. And so by doing this here, notice here I'm making sure that I'm not capitalizing the first letter. And as we saw earlier, that's important. This way, this is still classified as being a type of list as opposed to a type of new list if I capitalize the N. And again, you might see, by doing that, you could run into problems. But if I just want to create a list, this is how I can do it, an empty list. Again, notice this list is just being created, or this particular list, this slot for the list is in the lobby, because there's no object I'm creating it against. So I can also use a list method to do the same, and while I'm at it, do that. I can append stuff to a list. So maybe I hadn't done this step, or had done this step and wanted to append. Either or, doesn't matter. Maybe I just created an empty list and then appended. So yeah, append an item. I can print the size out. I can get an item at index. It's zero index, the lists in here, as they are in a lot of languages. I can get an item at a given index. Oh, sorry, I say set. Yeah, so I can get an item at an index and I can set an item. So at gets it at puts it at a certain position. Again, the given index, zero index. I can remove an item. I can insert an item at a given index as well in there. And then I can have a look at our list. So I encourage you to play around with this when you're using insert and put, and just seeing what it does to the list. I'm just making sure, yeah, that is actually inserting it and pushing it around, so to speak, just so you can see what's going on. And yes, a list can contain a list as an entry. And I'm assuming you can have a list of a list of a list if you really want to. But again, experiment. So there's a number of things that are useful to use with lists. things like for each, and there's 3 forms to for each. In fact, there's 3 forms to everything we're going to look at. So first up is for each. So suppose we've got a list, ham, spam and jam, and we just called it our test list, and it's of type, guess what, list. So for each, this is the sort of biggest maximum qualified way, and you'll see how it's horses for courses. So here, I want to utilize the index and the value here, so I'm using this specifically for that. So how it works is, here's my index, here's my value, and then I'm getting it to then write. Oops, let me go back there. Clicked on accidentally, yeah. So index value expression. There's the index, the value, the expression. There's a form I can use where I can remove the index. And in this example, it's going to print out the index, colon, value, and then a comma. And I'm using right here, so it will just keep carrying on, and it will do that for each thing. So I'll get index 0, ham, in this form, and then a comma, and then again for spam, 1 and spam, and then again, and then 2 and jam. I can remove the index in the expression, so this is the second form, and so it'll just iterate through, again, going through each one. So this is quite useful if you just want to, say, print out a load of values. So here I've got this, so this is just the index and the expression I want to execute. And then finally I could just use the expression. So it's like doing this but without explicitly saying value, but it does the same thing. So again, depending on what you want to leverage, these are going to be, your choice is going to be based on that. You might find that there's not a lot of difference between this and this, and you might find yourself going for this. But this one, you can see, because of the presence of the index as well, has more use. Of course, these could be anything. I could have this as I and V, as long as I correctly use them. Same here, this could be V. It's just a convenient name label that I'm using to do that, to do the iteration. There's a select in here, which may be, more useful for what I'm trying to achieve. These return new lists. So in this example, all of these do the same thing. They take this list, and you can see they're applying the is odd onto the list. So they're iterating through index value is odd. That's one form. Another form, I can just lose the index. Another form, I can lose the index and the value. For this example, they're all going to print the same thing. But again, there may be instances where for some reason you might want to be doing something with the index within here. Like very similar to the other one. So within that expression region. So what's happening is, if you like, every time we simplify this, as we move down the 3 forms, our expression is the only thing that remains. And so what we're doing in our expression is going to dictate, I think, what form we choose. I suppose that's how I would think about it. If you want to do the same operations in place, because this is actually creating, albeit on the fly, and returning a new list, which is the new list which is actually being printed. The underlying list is not being altered. If I wanted it to do it in place, then I can use select in place instead. And then we get this map form. So here with map, this is where I want to do something on my values. So again, I've got a list in this form, index, value, expression. So here my expression is just I'm adding value to the index. And then what it's going to do is it's going to return, because I'm doing print line here, it's going to create a new list on the fly. And it's going to take the value and just add the index to it. So this will be 0 plus 1, this will be 1 plus 2, and so on. That's just for the purpose of illustration. This one does a slightly different thing, but what I've done here is I've removed the index in this form. Now the form doesn't have any index, doesn't need it, and here I'm just working my way through the value and multiplying it by 2. So it's going to be 2, 4, 6, 8, 10, 12. And then finally I can simplify this one further still down to this, and I'll get the same result. So again, you just pick the three out of the choice of the 3 forms based on whatever you're doing in your evaluation. What does it need? You know, what slots, what values, what things, you know, what messaging is going on inside there that is going to need these other components, and just deciding accordingly. And as with the previous one, you can do the same operations in place, so it doesn't create a new list if you want to. Map in place. Okay, to add confusion here, there is specifically something called maps. So you saw that we had a map method, I suppose, that we can apply to lists, but there is also something called maps. So in IO, maps are hashes, so the collection of key value pairs. Not surprisingly, there's a map object that you can clone to create a map. Here we've got a map called servitor, and we can print out, just check what type it is out of curiosity, and no surprise, it's a type of map. We can do the slot thing, and if at this point we do check for slots on here, it's going to be actually empty. What you'll notice is when you're checking for slots on like clones, it won't return, it'll only return the things that were created against that clone. It doesn't show you, using slot names, slots that might be coming down from map. You'd have to check map to do that. So what I can now do is I can start putting key value pairs onto my map. So I can use the output to do that. So supposing I wanted to put type and mouse in there, I can ask it what value is at the key type by doing this. I can put more on my map, on my hash, so I can have another key value pair of name and then Dave. I can get it to print the object name, so the specific name of the object as IO is created for you, and its contents, like what key value pairs it contains. If I want to, I can just ask it to list what's on it, and if I do that, I get a list of lists where the list of the list are key value pairs, but done like this. Or I can actually get it to list the keys like this. I can also ask it the size here, which I believe would return 2. If I'm just looking at down on my notes off here. For some reason I opted not to put that in the comments section on there. But yeah, so that'll tell you basically the size of that list. Yeah, 2. Because there's 2 lists on the list. Ranges we did see earlier actually. So it's a container containing a start and end point and instructions on how to get from the start to the end. But you don't always see that. It's abstracted away. And it's something I really only stumbled across while I was putting together this. So I've not gone down the rabbit hole very deeply. You can see here it's pretty straightforward. This particular one is just going to print the numbers from 1 to 5. So there's my range. There's the range bit. So I'm sending this for each message, which in and of itself has messages inside of it. So it's going through the values in each one and printing this. You probably can work out maybe how this can be simplified or made more complicated from what you've seen so far. But yeah, 1 to 5. In fact, yeah, what's happening here is the message to 5 is being sent to this. So we're sending this to this is a number object. If you were to ask it to ask it what the type of 1 is, it will be a number. So numbers just work out of the box. I would definitely check out the IO guide on the IO website about the range protocol, because there's instructions on there about how you might want to extend that functionality to other objects and the ways in which you can do that as well. But I'm not competent enough or confident enough to really talk about that. So I had a go on the fly for this video, but decided against it. So writing text files, something I seem to do an awful lot of. Pretty straightforward, I think. I mean, there's probably quicker ways of doing it in other languages, but generally pretty simple. So notice I also haven't had to install any libraries as well. So I'm creating an object here, or cloning the file object. But notice there's no here, which is interesting, is that, okay, so this is of a certain type. And again, if you were curious, you could find out what type this is. But you can see here, the layout's maybe slightly different, and I'm not explicitly saying clone here. So I've got this file slot, again, creating the lobby, and creating it, assigning it with this. So this is just, assigning this to say, I'm going to be, I'm just going to be opening this file in a moment. So this is the file I'm interested in. So now I can interact with this. So I can ask it to remove the file if I want to delete the file if it already exists. I can open the file for updating. So because once I've created this file slot, I can send messages to it. So yeah, remove message, and remove that file, whatever I've got on this slot. I can open it for updating. I can write, and so now I can write to it. So I can just write stuff to the slot, and I can close it. Yeah, always remember to close. The methods open for appending, open for reading, open for updating are used for opening files. To erase an existing file before opening a file, the remove method can be used. Just as a reminder. So they're the 3 main ones that are on. Again, you can sort of check the methods that are available by interrogating the appropriate objects in the system, appropriate slots or whatever, using the appropriate methods. Now let's see how that works with CSVs. So here again, first bit's the same. Open for updating. I could probably, well, I know I could because I've done this before. I just put this in here for the benefit of showing you the remove command. In the case of for updating, you saw that there was two ways. So for appending and for updating, I could actually remove, not have this, and it would just overwrite what was already there anyway. Because I tried it and it worked when I did it, but I just wanted to include this just to show you that there is a remove function in here, or remove method, should I say. Yeah, so same as before, but here's slight difference. So when I write the particular things, I just need to make sure I'm including the comma separators. That's the quick and dirty way I've done it. Obviously, again, what you could do is build up this write. So again, it's sending this write message to this file object. So here it's writing this, here it's writing this, here it's writing this, and then I'm closing it. If I want to read files, read text files, then again, create this file object. There's my message, I'm sending it. The message I then send the file object is open for reading. I can then get it to read the file to the end, so I send it this read to end message, and it just dumps the result into a slot I've called content here. So again, creating and assigning that to the content slot. I can then close it, and then the content slot holds the text content of the file, so I can just print it and process it as required, whatever was in there. The content of the file is new line, so, and I could do it other ways as well. We'll talk a little bit about input output in a moment specifically, but I've been sort of slowly introducing you to write and print ln as we've been going along, so you probably grasped it already. Reading CSV files. So probably a number of ways you can do this, but the way I did it sort of out the box is this way. I didn't really go through extensively to see if there were specific methods for dealing with CSVs. I couldn't find any on first pass through, so I just created, my own stuff on the fly. Again, what I could do, if I was doing this a lot, and it would be sensible to do, is create this as a method on the specific object as a slot. So again, file object, sending it that message, sending it open for reading, getting the content, same as before. So everything's the same up till now, but then what I do with it, so everything's in that content. So now what I can do is split content by new line. So I end up with these lines. And again, if you're curious, it's a bit of homework. You could run this code, find out what is lines, what's it actually create, because again, it's doing this dynamic typing. So what sort of thing is that? What type is that slot that it's created? But clearly, I can iterate through this using for each. So for each line in lines, sort of like that, isn't it? Similar to other languages that do that. So I'm going through, and on the line, I'm taking line and further splitting that into values on commas, and then for each of those values, for each value in values, I am writing them out. And if I do that, the way this is configured, or the way this is sort of set up in the loop, and the fact that there might be, certain things there, and bearing in mind what I put in before, that was going into my, let me just skip back a couple of times. So that was what was in there. This is going to get printed out in a certain way. Now the way this is it will just print each of the values on a separate line because I'm using write ln in here. Yeah, so difference between write and write ln, one is with, one is without. I don't think I want to say anything more about that at the moment. I don't have any other notes, I don't think. Yep. So now, input and output generally. We've sort of seen bits of this and we can get a feel for this. So, supposing I want to do the classic, get a name from the standard input and then just say hello back to the screen. Pretty much one of the earliest things you learn in programming, but I've saved it to the end just because I wanted to get objects and methods out of the way. So yeah, I'm just prompting to please enter your name. The print I'm using here doesn't have the ln at the end, so that's just going to be no new line. So I've got a gap here, so it just looks neat, and it's going to start prompting me for something. So I'm going to put in my thing. It's going to take that and using these various components from I/O, methods and such like, and objects, it's going to send that all as a message to the name slot, which is just created and assigned all of this stuff. So I'm just going to get back what I typed in essence, and then I'm just going to print that. Here I'm using these as concatenation symbols in the language. And again, you might want to just interrogate these and see what forms these are taking. If I use this form of print ln, I just can make sure I get a new line at the end of this. So if I then go on to print something else or do another prompt, it doesn't just carry on from where it left off. I could equally do it this way. So same thing up here, same thing here, but use write instead. So it almost looks like the reverse. And that does no new line. When I've been playing around with the language, I've been using this quite a bit. I don't know if it's idiomatically correct for the language, but that creates a blank line. If you just need to do it out of the blue without a combination for anything else. Obviously, if you were laying something out, you'd want it all sort of incorporated into your other stuff. But sometimes when I'm laying out code, where I've got multiple bits of code and I just want to put in a blank line before I have more results coming to the screen, particularly in the sandpit IO file, I'll sometimes have a load of these in different spots to just space results out. But yeah, so you can just play around with these, print ln, write. You saw earlier there was also a write ln as well, so that's write but with a new line. And again, where you would use these is really dependent on your use case. One thing to be careful of is doing this if you don't include the brackets here. Because of the way messaging works, if you try this, it will just print this and actually it will ignore the rest of the code. In some instances, I/O does a pretty good job of just ignoring things and not always creating like an error if it doesn't cause a problem at runtime, because that's when you pick up the errors. When you in runtime, it's an interpreter, and when you run it, that's when you get the errors. So if we run the code, it'll just do as much of the program as it can until it finds an error, and then it will print up an exception or some sort of error code with a fairly succinct but informative answer, and you just have to sort of decode it, and it'll give you the line it occurred and a few other things as well, and the type of object you're trying to do it on, and if it's a thing you're not supposed to do on that object, and so on. Because a lot of the mistakes you'll make is when you're sending an inappropriate message, or you're using something that isn't a slot, or that sort of stuff, to objects or on objects. Okay, so just a few very basic algorithms here. They're not supposed to be necessarily the most efficient way of doing things, but for consistency across the episodes, I wanted to have the same algorithms I talk about every episode, so you can just get used to seeing code shapes in the language. So yeah, here we have Euclid using the original, the OG subtraction method. It's not the most efficient method, but it's the subtraction method. And so you can see here, probably fairly self-explanatory now, you've seen quite a bit of code. We've got whiles and ifs, and here's our return here. We're not having to put in the return. And this is the form it would take. So here's my method, here's my first value, here's my second value. So yeah, I'm applying Euclid's algorithm to that. Here's the modulo method. I've used specifically temporary slots here that I've created, but equally there's possibly ways in IO as you get into language of refactoring this that use specific methods which could maybe simplify this, because in Ruby there is a quick way to do swap one value with another, but I've sort of spread it out here while I'm still playing around with the language. Linear search, again, not the most efficient form of searching, but just so you can see how that might be achieved in IO. So we take an array and we just search the array for a certain value and get it to return the index where it is. So again, 0 index, so this is index 2, and we're just creating this slot, which is a method, and that would reside in the lobby. And then going through, doing a for each. There's our index, there's our element, and then there's the message, which is a condition in this case. It's checking to see if the element on the array is the same as the value we're checking for, and if it is, just returning index. And there's a nil return here as well, just in case things go spectacularly wrong. Well, actually, yeah, if it doesn't find anything, it's returning nil. Oh, good old bubble sort. Again, not necessarily the most efficient thing, but you get the picture. So this looks probably the most straightforward, and to me, just the way it's laid out, it looks closest to a lot of other languages. Although, of course, in this language, because of the way the for is constructed, it lays out slightly differently with the brackets than maybe fors in other languages. But at the end, it depends on what languages you're working in as to how your for loop actually looks. And so with this one, we have our for with the starting components. So our count, where we're counting from, where we're counting to, and then the bit we want to do, which has been indented down here. Same again for the inner loop, and then the bit that would be here, which is the rest of this, indented down here. And then we have our if with our condition, and then all the things we want to do as a result of that condition. And then ultimately we're returning the array back here. And here we're using the sort of the at-put stuff. So there's a number of array methods that we're using. And then we're printing it, and that's what it would come out if we printed it. So stuff to try. I/O is a highly dynamic and introspective, so there's lots of ways you can change the behaviour of the language during runtime. Changing the syntax of I/O and changing of the behaviour of I/O is another thing to try out. Because it's incredibly customizable. Also, concurrency is worth exploring through coroutines, actors, futures. That was actually covered in the 7 Languages by 7 Weeks chapter, as was changing the syntax and changing the behaviour. We looked a little bit about changing stuff, and we looked at the operator table, but it wasn't a rabbit hole I wanted to go down in this video because it's huge and I'm still playing around with it. And also check out exceptions with methods such as raise, try, catch and pass if you're familiar with exceptions in other languages. And then finally a note about GitHub. Remember to check out the I/O files I have uploaded to GitHub. Here's where it is. If you go to the GitHub page, and I'll include a link to the GitHub page, I'll include a link to this as directly as I can. It's in all of the stuff I've talked about in this episode are in the Sandpit IO file in that folder. And like I said, links to these and other resources are in the video description, along with links to I/O language resources and setup instructions to start coding in I/O. I'll include a link to that video I did about setting up for I/O, or I did actually do a video because there are a few weird things you need to be aware of. If you find this series useful and think others will find it useful, please share it. And you should have enough information now to just get started if you're curious. And so now it's time to code to learn. Thanks once again for watching. Bye for now, and I will catch you in the next episode.